So we have seen how a Smith chart essentially shows the complex reflection coefficient in a complex plane, but instead of two curves which are constant resistance curves and constant reactance curves. What you see here is an enlarged Smith chart, and let's see what are these two curves all about. First, we see full circles in the Smith chart. Those are called as constant resistance curves. That means as long as I am traveling along that particular curve, my resistance doesn't change. All that changes is the reactance. My resistance is fixed. For example, what you see here, the center of the Smith chart is 1. As I travel along that particular circle, my impedance values will have only the reactance changing, but the resistance is going to be just 1. The normalized resistance is going to be just 1. How about the other curve? The other curve is called as the constant reactance curve. We know that the resistance is the real part of the impedance and reactance is the imaginary part of the impedance. So these curve segments are called as constant reactance curves. If I take a particular curve and move along that particular curve, all that changes is just the resistance but not the reactance. The reactance remains a constant. So how do I read the reactance and the resistance? The Smith chart gives those values along the rim of the Smith chart where you can read the reactance, and along the center line of the Smith chart where you can read the resistance. So the center line, which is along the x-axis of the reflection coefficient, the center line where the reflection coefficient is purely real, that offers pure resistance. The leftmost half is the reflection coefficient of -1. The center point is the reflection coefficient of 0, and the rightmost point is the reflection coefficient of +1. We know that a short circuit offers a reflection coefficient of -1. If you look into the Smith chart, the resistance value that you read from there is 0. The reactance is 0. The resistance is 0 and the reactance is 0, as it should be the case for a short circuit. How about the other end, the right hand end, which is +1, a reflection coefficient of +1, where that corresponds to an open circuit, which means the resistance is infinity while the reactance is 0. The point at the center of the Smith chart is called as the matched impedance or the characteristic impedance. But before we go into that, the upper half of the Smith chart is positive reactance. All the values that you see in the rim of the Smith chart is going to be a positive number that keeps increasing to infinity all the way here, starting from 0. A positive reactance, we know an inductor gives a positive reactance. So it is said that any point on the upper half of the Smith chart is an inductive load. It has inductive effect in it. Similarly, the bottom half of the Smith chart is the negative reactance region. The negative reactance region, all the numbers in the rim are going to have a negative in it, and we know that the negative reactance is offered by a capacitive load. And again, the center point of the Smith chart is really the matched impedance of 50 ohms, the normalization impedance that we use, which is typically 50 ohms. When you are at this particular point at the center of the Smith chart, the bullseye point, you say that the load is perfectly matched to the feeding transmission line. So as a summary, a Smith chart is able to simultaneously represent both the reflection coefficient as well as the load impedance for a certain characteristic impedance that is feeding that load.